moon, perhaps, or, drop something, and just wondered about the invisible forces doing the work. Why does an apple fall downwards? What keeps our moon circling the Earth? And what drives those huge ocean tides, the ebb and flow? These aren't just, random things happening. They point to really fundamental forces. Welcome to the Deep Dive. Today, we're diving into gravitation and some other key concepts about forces in classical mechanics, too. It's a really crucial area. This session is designed specifically for you, especially if you're preparing for academic exams or maybe competitive tests like UPSC, SSC, things like that. Or maybe you just want a clearer grasp of these physics principles. Our aim, to break down the essential knowledge from our source materials, make it crystal clear, concept-driven, ready for your success. We're basing this on a comprehensive science text, so the information is precise and exam relevant. So, let's jump right in. It seems a bit strange at first, doesn't it? An apple falling, the moon orbiting. How could one single force link those two?
It's a fantastic question. And what's truly brilliant is Isaac Newton's realization. He saw the connection. He understood that the very same gravitational force pulling the apple down is also what holds the moon in its path around the Earth. He actually pictured the moon as constantly sort of falling towards Earth at every single point in its orbit. Instead of just shooting off in a straight line, gravity keeps pulling it inwards.
Falling, but never hitting us. That's quite a concept. So how does that circular motion actually work? How do we visualize it?
Well, think about whirling a stone on a string, around your head. To keep it moving in that circle, you have to constantly pull inwards on the string, right? Towards your hand. That inward pull, that's what physicists call the centripetal force. It literally means center seeking. It's this force that continuously changes the stone's direction, causing it to accelerate towards the center, even if its speed stays the same. For the moon, it's Earth's gravity that provides this exact centripetal force, pulling it, keeping it on that curved path.
Okay, that analogy helps. Now, something people often ask is, if Earth pulls the apple, does the apple also pull the Earth? And if it does, why don't we, see the Earth zoom towards the apple when it falls?
Ah, yes, an excellent point. This ties directly into Newton's third law, action-reaction pairs. So, absolutely, yes, the apple does pull on the Earth with an equal gravitational force, but, and this is the key, we don't see Earth move because of Newton's second law. Remember, ASHMA, or acceleration equals force, divided by mass. The Earth's mass is just unbelievably enormous compared to the apple's mass. So while the force is mutual, the acceleration Earth experiences is incredibly, incredibly tiny, imperceptible. The same logic applies to the Earth and moon. They pull on each other, but Earth's movement due to the moon's pull is negligible because Earth is so much more massive. This attraction applies to everything.
Right, so it's a real force, measurable, acting everywhere, not just a concept. How do we define it precisely mathematically?
That brings us to the universal law of gravitation, a real cornerstone. It states that every object in the universe attracts every other object, and the force is directly proportional to the product of their masses. And, crucially, inversely proportional to the square of the distance between their centers. The force acts along the line connecting those centers.
And the formula. How do we calculate this force?
The formula is F equals G times M, all divided by D squared. F equals GMMD. So here, M and M are the two masses, D is the distance between their centers, and G, that's the universal gravitational constant. Its value is very, very small. About 6.673 times 10 to the power of minus 11 Newton meter squared per kilogram squared, NMTAG. This tiny value tells you gravity is quite weak unless you have really huge masses involved, like planets or stars. Henry Cavendish was the one who first measured G accurately.
And the universal part really means universal, applies everywhere.
Exactly, that's its power. It applies to any two objects anywhere in the universe. Doesn't matter if they're celestial bodies or tiny particles on Earth. And this single law explains so much. First, the force binding us to Earth, obvious, but fundamental. Second, the moon's motion around Earth. Third, the planets orbiting the sun. Fourth, even the tides, the pull of the moon and sun on our oceans. Just to give you an idea, the force between Earth and the moon, it's calculated to be around 2.02 times 10 to the power of 20 newtons. A massive force.
Wow, 10 to the 20, that's huge. Okay, let's bring it closer to home. Objects falling near Earth. What do we mean by free fall?
Right, free fall is when an object is falling only under the influence of Earth's gravity. We ignore air resistance for the pure definition. In this ideal state, the object accelerates downwards constantly. We call this acceleration g, the acceleration due to gravity. Its unit is meters per second squared, MSO.
And how do we find the value of g here on Earth?
We can derive it from the universal law. Think of an object with mass MAF near Earth's surface. The force on it is its weight, equal mg. But the universal law also gives the force as equal ngm_r1, where m is Earth's mass and r is Earth's radius. Since the object is near the surface, d is approximately r. So we set them equal. mg equals gmmr. Notice the object's mass man cancels out. This leaves us with g equals gmr1, 4. A really important result. If you plug in the known values for g, Earth's mass, about 6 by 124 kilograms, and Earth's radius, about 6.4 by 106 meters, you calculate g to be roughly 9.8 meters our way. You'll use this value, 9.8 meters RS, a lot in problems. Oh, and one more point. G isn't perfectly uniform everywhere on Earth because Earth isn't a perfect sphere. It bulges a bit at the equator and is flatter at the poles. So the radius is slightly smaller at the poles. Since G r1, a smaller I means G is slightly greater at the poles than at the equator. A subtle point, but important for precision.
Okay, 9.8 meters are. But wait, if g is the same for all objects near Earth, why does a feather fall slower than a hammer? My experience says they don't fall together.
That's a very common observation, and you're right. In everyday life, they don't. But the reason isn't gravity itself, it's air resistance. In a vacuum where there's no air, they do fall at the same rate. Galileo famously showed this, or at least the principle. Heavy object, light object, drop together, hit the ground together, assuming no air resistance. A feather has a large surface area for its small mass, so air resistance slows it down much more than it slows down a compact hammer. Remove the air, and they accelerate identically at 9.8 meters dollars. For your exam calculations involving free fall, remember you can use the standard equations of motion. Just replace the general acceleration a with g. So v u plus gt, s is plus 12 gt2, and v equals u plus 2 g's. And be careful with signs. Conventionally, g is positive if motion is downwards, negative if the object is moving upwards against gravity. These let you solve problems like, say, a car falling off a cliff at speed just before impact, or how high an object goes when thrown upwards.
That clarifies free fall very well, thank you. Now, let's tackle something that often confuses students.
Yeah.
The difference between mass and weight. Can you break that down?
Absolutely. This is fundamental and often misunderstood. Let's be very clear. Mass is an intrinsic property of an object. It's essentially the amount of matter, the stuff in it. More technically, it's a measure of its inertia, its resistance to changes in motion. The crucial thing about mass is it's constant. Your mass is the same on Earth, on the moon, in deep space. It doesn't change with location. Weight, however, is different. Weight is a force. Specifically, it's the gravitational force exerted on an object by a large body like a planet or moon. We calculate it using W, it's mag. Mass times the local acceleration due to gravity. Since it's a force, its SI unit is the Newton, N. And because it's a force, it also has a direction always acting downwards towards the center of the planet or moon.
So mass constant, weight variable. That's the core difference.
Exactly. Your mass never changes, but your weight depends on where you are because G depends on where you are. We already saw G vary slightly even on Earth, but compare Earth and the moon. The moon has much less mass than Earth and a smaller radius too. This results in a much weaker gravitational pull on its surface. The value of G on the moon is only about 1.62 meter-newtons, roughly 1/6 of Earth's G. So an object's weight on the moon is about 1/16 of its weight on Earth. If you weigh, say, 600 newtons here, you'd feel much lighter on the moon, weighing only about 100 newtons. Your mass, remember, would be exactly the same.
That 16th figure is a classic exam point, isn't it?
Correct.
Good to remember. Okay, let's shift focus a bit. We've talked about gravity pulling down. What about forces acting on surfaces? Like why can camels walk on sand easily? Or why do buildings need wide foundations?
Right. This brings us to thrust and pressure. They're related but distinct. Thrust is simply the force acting perpendicular or normal to a surface. If you push down on a table, the downward force is the thrust. Pressure is about how concentrated that thrust is. It's defined as thrust per unit area, so pressure, thrust area. The SI unit for pressure is newtons per square meter, NMLA, which we also call the Pascal, symbol P.
So it's not just the amount of force, but how spread out it is.
Precisely. The effect of a force can be dramatically different depending on the area it acts over. Apply the same thrust over a tiny area and you get very high pressure. Spread that same thrust over a large area and the pressure is much lower. Think about a drawing pin or a thumbtack. You push with your thumb a moderate force, but that force is concentrated onto the extremely sharp point. This creates enormous pressure, enough to easily push the pin into a notice board or even wood. Or consider walking on loose sand. When you stand, your entire weight, the thrust, acts on the small area of your feet. High pressure, so you sink. But if you lie down, the same weight is distributed over a much larger area of your body. Lower pressure, so you don't sink as much. This principle is used everywhere. Camels have wide feet, Larger area reduces pressure on sand. Army tanks use wide tracks for the same reasons, spreading their huge weight. Trucks often have double or wide tires. Cutting tools like knives have sharp edges to maximize pressure for a given force. And building foundations are made wide to minimize pressure on the ground, preventing sinking. It's all about managing pressure through area. And just quickly, fluids, liquids, and gases also exert pressure on the bottom and sides of their container. And this pressure acts in all directions.
Very clear examples. Okay, moving from solid surfaces into fluids, why do things feel lighter in water? And how can massive steel ships float? Seems counterintuitive.
This involves another important force, buoyancy, sometimes called upthrust. Buoyancy is the upward force exerted by a fluid, liquid, or gas on any object immersed in it. You can feel it easily. Try pushing an empty sealed plastic bottle down into water. You'll feel the water pushing back upwards, resisting you more and more as you push it deeper. That's buoyancy.
So floating or sinking is it's a contest between weight pulling down and this buoyancy pushing up.
Essentially, yes. It's the balance between the downward force of gravity, the object's weight, and the upward buoyant force exerted by the fluid. The deciding factor in this balance is usually density. If an object's average density is less than the density of the fluid it's in, the buoyant force will be greater than its weight, and it will float. Think wood in water. If the object's density is greater than the fluid's density, its weight will overcome the buoyant force, and it will sink, like an iron nail in water.
Density is key then. But can we know the exact size of this buoyant force? Is there a rule for it?
Yes, there is. And it's a principle discovered over 2,000 years ago by the Greek mathematician Archimedes. It's Archimedes' principle, it states. When a body is immersed fully or partially in a fluid, it experiences an upward buoyant force equal to the weight of the fluid that the body displaces. So the more fluid an object pushes aside, the greater the upward buoyant force on it. You can demonstrate this. Hang a stone from a spring balance, note its weight in air, then lower the stone into water while it's still on the balance. You'll see the reading on the balance go down. The stone appears to weigh less. That apparent loss in weight is exactly equal to the buoyant force, which, according to Archimedes, is equal to the weight of the water the stone displaced.
Ah, the eureka moment principle. I remember the story of Archimedes in his bath. What are its modern uses, besides checking gold crowns?
Haha. Yes, the Eureka story is famous, but the principle is incredibly important in engineering and science today. It's fundamental to designing ships and submarines. A ship floats because its hull displaces a volume of water whose weight is equal to the entire weight of the ship. Even though it's made of steel, its overall shape creates a low average density. Submarines use ballast tanks to take in or pump out water, changing their average density and thus controlling their buoyancy to dive or surface. It's also used in instruments like lactometers. They measure the density of milk to check its purity based on how deep they float, and hydrometers, which work similarly to measure the density of various liquids. These are very practical applications you might encounter. So just to quickly recap our main points today, we started with Newton's universal law of gravitation, that universal attraction between all objects. Then we looked at free fall, defined the acceleration due to gravity g, saw how to calculate it, and noted its slight variations. We carefully distinguished between mass, which is constant, and weight, which is the force of gravity and depends on g. Remember the 16th weight on the moon example? We then moved on to thrust, force perpendicular to a surface, and pressure, thrust per unit area, understanding how area affects the impact of a force. And finally, we explored buoyancy, the upward force from fluids and Archimedes' principle, which quantifies that force as equal to the weight of the displaced fluid, explaining floating and sinking.
That's a fantastic summary, and it really highlights how these concepts, from gravity holding galaxies together to buoyancy floating a ship, are interconnected and essential. They form the bedrock of classical mechanics. Understanding them isn't just about passing exams, though it's crucial for that. It's about understanding how the physical world around you actually works. A solid grasp here is invaluable. Stay tuned for more exam-ready insights and concept breakdowns. Please do subscribe so you never miss a topic. In this deep dive, we covered the following topics: gravitation, introduction, and Newton's insights. Gravitation, universal law of gravitation. Gravitation, free fall and acceleration due to gravity, g. Gravitation, distinction between mass and weight. Gravitation, thrust and pressure. Gravitation, buoyancy. Gravitation, Archimedes' principle.